volume, right? So let's write the volume first. 4 pi over 3 r cubed. And yes, I have to find dv, but I need to replace this r like I did with the circumference, with the area. So here's r. R is c over 2 pi. So this is 4 pi over 3, c over 2 pi, everything to the third power. And simplify it before I find dv. Is this clear? Any questions? Can you follow this? Yes, please, Joey.
Okay, so
I want to show something. The volume includes R. That's the formula for the volume. But I don't have any information about R. I only know C and I know DC. So from the circumference, which is 2 pi r, I have to solve for r, and we did, as c over 2 pi, and I have to replace r by c over 2 pi. So, like we did here with the area, we had to replace the r squared as c squared over 4 pi squared. So the same thing here. So we replace c by r by c over 2 pi. So then I continue simplifying. 4 pi over 3 times c to the third divided by 8 pi to the third. C to the third, 2 cubed, and pi cubed. I will simplify by 4, and I will simplify by a pi. So I get 1 over 6 pi squared times c cubed. Let me check. The 2, yes. The pi is squared, yes. 6 pi squared, c cubed. And only now I should determine dv, the differential of v. And remember, I have to have whatever times what? Thank you. So we have 1 over 6 pi squared times 3 times c to which power? We bring 3 down, we subtract 1 from the power, 2. Finally, dv equals 1 over 2 pi squared c squared dc. And yes, I have to plug in the numbers. 1 over 2 pi squared, c was 84, dc was 0.5. I put them in the calculator. So 84 times 0.5, that's 42. And divided by 2 is 21. And I have to divide by pi squared. I got 2.1277. Correct me if I'm wrong. Measurement unit. dV has a measurement unit. Very good. Any questions? Sorry. I forgot to square. Sorry about that. So it's 1 over 2 pi squared, 84 squared, and 0.5. Sorry. So multiply by 84. Correct me if I'm wrong. I got 178.73. Anyone checking my numbers? No? Yes? No?
I guess
Yes, Tom?
actually, since the derivative of the volume is the area equation, I'd use that instead of.
That's fine. Absolutely. But don't forget to put DC in there.
Right.
Did you get the same answer?
Maybe, I'm not even there yet. But
Oh,
I'm sure.
okay, I'm gonna calculate again, because nobody's checking my numbers, so times. Yes, you did? Very good. Yes, I did too again. Good. Finally, we're asked to find the relative error, which is dV over V. 178.73 divided by the volume. Here's the volume right here. We simplified it. So 1 over 6 pi squared times 84 to the third. No measurement unit because it's cubic centimeters over cubic centimeters. So 178.73, exactly what I just got before. Basically, it's multiplied by 6 and multiplied by pi squared, but divided by 84 to the third power. I got 0.01785, 0.017857, which is 1.8%. This was an application of differentials. Should we look at another example?
Yes.
Very good. I'm trying to find another. Okay, 33. On the same page, 255. The edge of a cube I'm going to call it X, was found to be 30 centimeters with a possible error in measurement, which is the notation.
Yes.
Very good. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume. Then in computing the surface area. Very good. So let's start with what? What do we start with? The volume of the cube, which is very good. So we're asked to find the maximum, to estimate, not find, to be exact, the error in the volume. What do I have to find? What are we going to find? Yes, which is dV. Very good. Which is?
X cubed plus.
What is I have to differentiate. This is the function that I need to differentiate.
3x squared
Times?
Times 0.1
dx. Right? Very good. I'm done. So this is 3, this is 30 squared, and this is 0.1. So 900 times 0.1 is 90. So this is 270. Measurement unit. Very good. Perfect. So this is the maximum error in maximum error in the volume triggered by a minor change in x, minor error in x. Good. So now let's determine the relative error. The relative error is 270 divided by 30 to the third power. So I got 0.01. No measurement unit. And what is the percent error? 1%. Very good. Now we want the surface. What is the surface area of the cube?
6x squared.
Perfect. I need to find the S. What will that be?
It's going to be 12x times x.
Perfect. I'm done. 12 times 30 times 0.1. So this is 36. Measurement unit.
Centimeters squared.
Awesome. Now we want to find the S over S, which is 36 divided by 6 times 30 squared. So 36 divided by 6 will be 6. So then 6 divided by 30 squared. I got 0.00666. So no measurement unit, and in percent, very good. Okay, so now let's go back to something else that we need to look at. Back to our same graph, same function. And of course, we're going to look at point. Which point? But this time of coordinates A and perfect. Of course, we're going to go back and draw the tangent. What is the slope of this line? Very good. So now we have a point, a comma f of a, and we have the slope, which is f prime of a. And I would like to determine the equation of the line. Equation of the tangent line at P. So please dictate. How do we find the equation of the tangent line at P?
Y minus f of a
Very good.
equals m
Yes,
f prime of a
perfect.
times x minus a.
Awesome. That's it. I'm going to move f of a to the other side. Have we seen this before? Only a few minutes ago. It's a slight deviation because now we're not really saying that the error has to be very tiny. It has to be small. But if we compare, let's go back and compare. So this is f of x, this is f prime of x, and this is the difference in x, x minus a. Okay. Here's the beauty now. Would you agree, before I write it, I want us to agree. If we're really talking about values close to A, I'm not talking about here, I'm not talking about here, but values very close to A like we did before, right? And this is the interval. And if you say, and this is the same thing with the cost, the actual difference costs of 201 minus 200, and the C prime of 200. Do you agree that if I choose a value here, and I want to determine f of this value. It doesn't really matter. It's not exact, of course, but it doesn't really matter if I use the graph of the function or the line, the tangent line. Now, if I'm here, the difference will be huge. And I will not be using this tangent anyway. I will be using this tangent if I want to approximate. But if I'm around P, very close left and right, left or right, if I use the function or I use the tangent, it's not going to be a big difference. And that's what this really says. And this is how we started today. And we said, do I find C prime of 200 or do I find C of 201 minus C of 200? And it doesn't matter because they're very close. So we will say that any differentiable function can be approximated by a line. Not any line, by the tangent line. Near A. So any differentiable function can be approximated by a line. We call that the linearization of a function. So this is called the linearization of a function using a line, using the equation of a line or a linear function. Better, I like to write that. Using a linear function. I'm going to erase that. But only near different points. Different function for different point. Let's look at an example, like number 3 on page 255. We are given f of x, which is the square root of x. We are given a equals 4. Find the linearization. The linearization is this. This is the linearization. Denoted by uppercase L of x. It's a function and it will be a linear function. So this is f of a plus f prime of a times x minus a. Can anyone dictate the first step? L of x will be f of, yes? Yes, we're going to put those in. Oh, that's exactly what it means. And this is the line that can be used to approximate the square root of x only near 4. And we mean it, near 4. Okay, so I have to find f prime of x, which is 1 over 2 the square root of x. F of 4, how much? 2. Plus f prime of 4. Perfect. Times x minus 4. This is the line. We still have to simplify it a little bit, but this is the line that approximates the square root of x when x is near 4. So this will be 1/4 x minus 1 plus 2 is plus 1. I should have not written it on the side. So this is L of x, 1/4 x plus 1. So let's write it in words. This is the line that can be used, or the linear function that can be used to approximate the square root of x near, only near, what? Yes. If I change 4 into 16, do you think that we're going to have the same function, the same line? No, of course not. It will be a totally different function. So in other words, I'm saying this. This is the graph of the square root of x. And let's say this is 4, and let's say this is 16. Near 4, at this point, we have the equation of the line, which is y equals 1/4 x plus 1. But at 16, we will have a totally different line that will approximate the square root of x near 16. Is that clear? Okay. So I think we should look at one more example from this, or more. Do we need more examples? Yes? Yes? Very good. So let's look at f of x equals x to the 4th plus 3ax squared for a equals -1. We're asked to find the linear equation or the linearization of f of x near -1. How do I start? I write L of x, which is f of a plus f prime of a. Very good. And this comes from using the point slope form for the point that we have, a comma f of a, and the given slope, f prime of a. Good. So I have to find what now? I have to find f prime of x, which is cubed. Very good. I have to find f prime of a, which is -1, before I put them in. And that would be negative -10. Very good. We have to find f of -1, which is so -1 to the 4th is 1. -1 squared is 1. So 1 plus 3 is 4. But f prime of -1 is -4 minus 6. Agreed? So then we have the linearization, or the linear function, that approximates the square root of x near -1. Ready? So what do I have to write? F of a, which is 4
minus 10 times f minus -1.
That's it. So the linear function that approximates the given function near -1 is -10x minus 10 plus 6 is -6. Minus 10 plus 4, I meant to write. So only near -1. If we move away from -1, then there is a different function, the different linear function that will approximate the given function there. Any questions? Any questions? Okay, so we still have time to finish. I just want to show you 3 more functions. I will only ask you to remember their derivatives, not the inverses and nothing else. And that's the end of chapter 3, and we can start reviewing for the test. Would you like to see another problem of the approximations or another problem with linear approximation or the linearization? The first one?
Yeah.
Okay. Okay, so the one with the error? Okay. Can I show you these 3 functions and then we'll come back? I just want to, okay. So let's finish the 3.11. So I'm hoping that you are caught up with the checklist. I'm really hoping. So I'm hoping that you can turn it in next week, yes? Okay. So there is also a big umbrella of functions called hyperbolic. Hyperbolic functions. There are 6 hyperbolic functions, there are 6 inverse hyperbolic functions, and so on and so forth. We're only going to look at 3 hyperbolic functions: hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and their derivatives. Okay? So how did they come up with this? Well, they looked at the functions that have a component of e to the x. So e to the x minus e to negative x divided by 2. And they looked and they graphed these, and we can look at the graph in a minute. And I also looked at e to the x plus e to negative x divided by 2. And the ratio of these two. So the ratio will be e to the x minus e to negative x divided by e to the x plus e to negative x. So when they graphed these 3 functions, here's what they came up with. This is the first one. This is the second one. And this is the third one. They said, okay, the similarities somehow with trig functions. And they said, okay, let's use a name for this, which is hyperbolic sine, S-I-N-H, hyperbolic sine. They call this one, what do you think? And of course, the ratio of these two, they called it. Yes, there is a secant, a cosecant, and a cotangent, hyperbolic functions. Let's find out using the differentiation rules. Let's find out either sine or cosine the derivative. Which one would you like to determine? Not with the definition, with the limit. Just which one? Okay, so let's say we want to determine hyperbolic sine prime. Well, this is going to be 1/2 in front, e to the x minus e to negative x prime. So the constant stays outside, I don't need it. So 1/2. When we differentiate e to the x, what do we get? Perfect. But now be very careful. When we differentiate e to negative x, we get e to negative x times the inner function prime. Negative e to the x with minus in front. What is this?
E to the x.
Oh, of course. I'm sorry. I just didn't copy it. Sorry. What is this? So everything is really the same. So hyperbolic sine prime is hyperbolic cosine. There is one change here. Hyperbolic cosine will not be like cosine prime negative sign, but also positive. The same. So that's the only difference. And what do you think hyperbolic tangent prime would be? Squared. Exactly. Oops. That's it. That's all I would like you to remember. Just these three. And yes, they have inverses, and then the inverses have derivatives. I only need this. And let's practice a little bit and then go back to more problems with the error. Let's look at 33. Where are these useful? I'm sure we all traveled different places and we saw the power lines or the phone lines. So you see, they could not fit anything better than a hyperbolic cosine. Nothing, no other function than hyperbolic. That's how they determine the length or the distance between the poles, to be safe. The other example is the ocean waves. It's another hyperbolic function. Okay, so let's just differentiate a couple of functions, and then we go back to more problems. This is the end of chapter 3. Okay, so let's look at 33 on page 263. We have h of x equals natural log of hyperbolic cosine x. We want to find h prime. When I differentiate log, I get 1 over hyperbolic cosine times hyperbolic cosine prime, which is hyperbolic sine. But how much is sine hyperbolic over cosine hyperbolic, or hyperbolic sine? That's it. Let's also look at, let's say, 38. Y equals hyperbolic sine applied to hyperbolic cosine x. Chain rule. The outer function is hyperbolic sine, the inner function is hyperbolic cosine. We want to find y prime, or dy over dx, not the differential. We differentiate the outer function first, and we get when we differentiate, very good, hyperbolic cosine of hyperbolic cosine times the inner function prime, which is, that's it. Should we look at one more? Very good. Let's say 34. We have y equals x hyperbolic cosine of 1 plus x squared. So we have y prime is first function, second function. So what do I write? The first function prime, hyperbolic cosine 1 plus x squared, plus the first function times the second function prime. Times the inner function prime, 2x. So I can rearrange it a little bit and write hyperbolic cosine of 1 plus x squared, and I put this in front as 2x squared hyperbolic sine 1 plus x squared. Now make sure you don't confuse hyperbolic cosine with regular cosine when you differentiate. Regular cosine prime is negative sign. Okay, do we need more with hyperbolic functions? Yeah, I would like to look at one word problem, quick, 51. In 51, we have a telephone line hangs between two poles, 14 meters apart, in the shape of a catenary, and this is the given function, where x and y are measured in meters. So we are given the function y equals 20 hyperbolic cosine of x over 20 minus 15 is outside. Okay. Find the slope of this curve where it meets the right pole. The right pole is when x is 7. So find the slope of the curve when it meets the right. So when x is 7, find y prime. So I'm going to differentiate and get y prime. What is that? So it's 20 multiplied by cosine hyperbolic is prime is sine hyperbolic of x over 20 multiplied by the inner function prime. This is 0 when I differentiate. Multiplied by the inner function prime, and I get, remember, x over 20 is the same with 1 over 20 times x. Very good. So I simplify, and I get that y prime is hyperbolic sine of x divided by 20. We're asked to find this when x is 7. Okay, so then I have sine hyperbolic of 7 divided by 20. How do I plug this in to find the answer? So let's do that. I am not sure if there is a hyperbolic sign in the calculator. However, I can always determine it. So I will put in parentheses, so outside 0.5, and in parentheses, e, right? I'm using the definition, e raised to 7 over 20 and subtract e raised to, in parentheses, negative 7 over 20. So when I got that y prime, when x is 7 meters, I got 0.357189. Second part of the question is it's asking us to find the angle theta between the line and the pole. So tangent theta equals 0.357189. How do I find theta? How do I solve this equation for theta? I apply something to both sides. What can I apply to both sides? Of course, thank you. So theta would be, careful now, if the calculator is in degrees, I will get degrees. Since the calculator is still in degrees, yes it is. I go to inverse tangent. One more time. Inverse tangent. I recall the previous answer. because I don't want to type it in. And I get 19.65 degrees. Is this clear? Make sure your calculator is in degrees. Otherwise, what you get is in radians. And you can change it into degrees, no problem. Is this okay? Yes? Okay. So now let's go back and look at one more problem for now, and we are going to I'm trying to find out the problem. Very good. 38. And that is on page 255. Let's read it together. One side of a right triangle is known to be 20 centimeters long, and the opposite angle is measured as 30 degrees with a possible error of plus or minus 1 degree. Use differentials to estimate the error in computing the length of the hypotenuse. And what is the percentage error? So first I have to draw a right triangle. It says one side of a right triangle is known to be 20 centimeters long, and the opposite angle is measured to be 30. So x must be 30, and with a possible error of plus or minus 1 degree, which will be definitely
Tx.
perfect. Use differentials to estimate the error in computing the length of the hypotenuse. I'm going to call it y. So we're asked to find, in part A, definitely we're asked to find Should I read the problem one more time? Very good, let's do that. One side of a triangle is known to be 20 centimeters long, so that's fixed. And the opposite angle is 30 with a possible error of plus or minus 1 degree. Use differentials to estimate the error in computing the length of the hypotenuse. So what am I asked to find?
dy.
Of course. This is our question. We have to find dy. But I can find dy before I find a relationship between y and x. So what trigonometric function will use 30 and 20 and y? Very good. So I have to write sine 30. I'm sorry, I have to write x, because that's what x is. Sine x equals 20 divided by y. I have to cross multiply and solve for y. So y times sine x equals 20. Y equals 20 over sine x. Better, y equals 20 times sine x to which power? Not to be understood as being sine inverse. Careful. It's not sine inverse, it's just sine raised to negative 1. Okay, so I have a relationship that connects y and x. Perfect. So now I'm ready to find dy, but I cannot forget to write something at the end. Perfect. So maybe to be exact, maybe I should write it like this, because I don't want you to think that this is sine inverse. So I put parentheses around sine and I put the power outside. So this is not arc sine. Okay, ready? So let's differentiate that function. I have 20. I bring down -1, so that's -20, times sine to which power? Which power? -2. From -1, I have to subtract 1. I bring down -1. I subtract 1 from the power. And times the inner function prime. The inner function prime. Remember, we are differentiating the power. One more time. This is a function raised to a power. I bring the power down, I subtract 1 from the power, and I have to differentiate the inner function. Yes. No, this is just cosine. Cosine x times dx. Is that clear? Because of the power. Okay, so in short, this is -20 cosine x over sine x squared dx. Now all I have to do is plug it in. So dy equals -20. How much is cosine 30? It's not 1/2 because sine 30 is 1/2. It's the other one. Very good. The square root of 3/2 over. The denominator is 1/2, but I have to square it. So I get 1/4. And then this is plus or minus 1 degree. Okay? No degrees in calculus. So I have to write pi over 180. Times dx, which is pi over 180, plus or minus. So I would like to simplify before I put in the calculator. So I have 10 here, and when I flip, I have 40. And I don't need that. Okay, so I have dy equals 4 minus in front 4, the square root of 3 times pi divided by 18. So I simplified by 2, I simplified by 10. I still have the square root, I still have the 4 that I have to flip and the pi. So let's see what we get. So -4, the square root of 3 times pi over 18. Any questions? Any questions? So 4, the square root of 3, outside pi, and divide by 18. And it's negative. It's positive or negative. So it's 1.2, approximately negative or positive, because we can put plus or minus 1, right? Positive or negative 1.21 approximately. So the differential, so estimate the error in computing the length of the hypotenuse. So when there is a change or an error in this angle of plus or minus 1 degree, there will be an error in an estimated error in computing the length of the hypotenuse of plus or minus 1.21 centimeters. And finally, we're asked to find dy over y, which is the relative error. What is the percentage error? But I have to start with the relative error. So dy is plus or minus 1.21. And y is this. 20 divided by 1/2, so it's 40. When sine x is 1/2. So the relative error, percent error, would be 1.21 divided by 40. So it's 3.025, so 0.03025 or 3.025%.